Today we are going to measure propeller RPM using sub $1 sensor. The sensor we are talking about is TCRT5000 reflective optical sensor. You can get it for less than $1 on Chinese websites. The device actually consists of two separate elements in a single packaging. It consists of a infrared LED and an infrared phototransistor. All this device does is just packages two of these components into a single packaging for ease of use. Here we take out the infrared phototransistor. As you can see, it's just like any other regular phototransistor. The LED is left in the packaging. We can use a multimeter to measure the functioning of both of these devices, like any other LED and a phototransistor. So let's try to see if this LED behaves like any other LED. We set up the multimeter to a diode mode. So let's reverse bias the LED to see if any current is passing through it. And no current seems to be passing through this LED in reverse bias mode. Now we do a forward biasing and we see that the current is passing through this LED. So it's behaving just like a normal diode, except that it produces infrared light when it's forward biased. Now in these multimeters, there is a option to measure DC gain of any transistor. And we can use that to measure the DC gain of our phototransistor. We set it up to the transistor mode. This phototransistor is an NPN type, so we plug it into the NPN socket of this multimeter. Now we see it's showing around a DC gain of 10. As we start turning this LED towards the light, as I start turning it towards the window, you can see the DC gain is increasing to 50 and 60. And if I even move it close to the window, it goes over 100. So we clearly see that this phototransistor is reacting to the infrared light. This has implications on how this device will be used. As now we see, it's affected by normal sunlight as well. So using it outdoors versus using it indoors will be slightly different, as outdoors it will be affected by bright sunlight. So again, phototransistor is reacting to the normal sunlight. Here is a schematic we use to test this device. Now we've connected TCRT5000 to our ESP32 running Arduino, and we are using the output of TCRT5000 and connected to the analog to digital converter of our ESP32. Here you see when we power it up, we can actually see the infrared LED lighting up. Now I'm using the white reflective, basically white paper, to reflect this light and see how far it can measure. And we can see the measuring distance is quite reasonable. It's reading from almost up to 3 inches the presence of an object. One thing to note here, this infrared LED, you cannot see it switched on with your naked eye, but the cameras do allow this infrared light to pass through. So you can actually see it with your mobile camera or with any other webcam that the infrared LED is actually switched on. Now I'm using a black battery holder to see how far its presence is detected, and we see that the distance is quite reduced. It's almost of the order of between 1 and 2 inches, which is fairly less as compared to the white paper strip that I was using earlier, which it was reading at around 3 inches. So the reflectivity of an object, as you would think, is an important factor in measuring the distance. So again, this white paper strip is almost 3 inches away, and the sensor starts detecting it, and the voltage starts dropping. But the black battery holder does not seem to be detected that far away. Now for Propeller RPM, I don't want to use this device in ADC mode because converting values to digital will take time from analog to digital, and I want to use it in a purely digital mode, in an on-off way. So here we've programmed it so it's going to digital input of ESP32, and I'm converting it into RPM, and I'm just testing it again with the white strip to see if this absence of this strip is detected as an RPM on this sensor. And the logic seems to be working. If you like the contents, do support our channel. So to measure RPM, I have put this device in an PCB with resistors to limit the currents to diode and phototransistor. Printed a 3D enclosure so that I can mount this device inside it, and the distance to propeller can be adjusted. It's a very simple 3D printed enclosure where the distance can be adjusted. Here are the two parts of this enclosure. Now the device is mounted inside the sliding part, and here you can see how it is mounted onto my Propeller RPM testing setup. As the propeller passes in front of this device, the distance between the device and the propeller can be adjusted by sliding the outer part in or out. And I'm increasing the distance. It seems a little bit too much, so I'll bring it out to reduce the distance between this device and the propeller. A little bit too close, so I'll push it a little bit in. Also, you've noticed that I've put white tape on the propeller. From our previous testing, we've seen white color reflects off much better and is detected at much larger distances. So in our testing, we found out that just leaving the propeller as is, it's a carbon fiber black propeller, the measurement of RPM is not that accurate, but when we attach a white electrical tape to it, it functions perfectly. So here the whole setup is now ready for testing. Let's just connect the batteries, prepare it for final testing. To verify the RPM measured by our setup, I will be using a Hanger 9 digital voltage and tachometer device to compare the RPM measured between our setup and a commercially available device. So let's start testing now. The digital tachometer from Hanger 9 measures in tens of RPMs. So whatever you see on that screen multiplied by 10. So we see both of these devices are tracking fairly closely, which is amazing for such a small and cheap sensor that it is functioning so well compared to a commercially available and rather expensive device. So there you have it, folks. If you want to measure RPM of any propeller, you can just buy a cheap sensor and make your own RPM measuring setup.